Welcome back, students. This is my fourth lecture on the topic vectors. In this lecture, we will see three-dimensional coordinate system, signs of coordinates of a point P in different octanes, and examples on it. Three-dimensional coordinate system, that is 3D coordinate system. We represent any point in space by an ordered triplet ABC of real numbers, where O is the origin and three directed lines through O that are perpendicular to each other are the coordinate axes. See diagram, student. Here x, y and z, these three vectors are mutually perpendicular. Now to study in detail the 3D coordinate system, I have invited to Professor von Schemwalk. Let us observe his lecture carefully.
Hello, I'm Professor von Schmohawk and welcome to YU. In the previous lecture, we saw how to construct a two-dimensional Cartesian coordinate system which allows us to graphically display ordered pairs of real numbers or sets of these ordered pairs as points in a plane. We did this by taking the Cartesian product of the one-dimensional number line with itself to form the two-dimensional Cartesian plane. In this lecture, we will construct a three-dimensional Cartesian coordinate system, which will allow us to display ordered triples of real numbers as points in three-dimensional space. The set of real numbers R can be thought of as corresponding to a continuum of points in one-dimensional space. It is this space which is represented by the number line. Each real number corresponds to a unique point in this one-dimensional space. We then created a two-dimensional Cartesian coordinate system by taking the Cartesian product of the set of real numbers with itself to form an infinite set of ordered pairs called R squared, or more commonly R2. R2 corresponds to a continuum of points in the two-dimensional space represented by the Cartesian plane, and each ordered pair of real numbers corresponds to a unique point in this two-dimensional space. However, we are not limited to forming Cartesian products of only two sets of real numbers. We can also form the Cartesian product of three sets to form the set R3. Just as the set R2 consists of ordered pairs whose elements can be any two real numbers, the set R3 consists of ordered triples whose elements can be any three real numbers. And just as the two-dimensional Cartesian plane was built from two number lines oriented perpendicular to each other, three-dimensional Cartesian space can be created by taking three number lines and orienting all three perpendicular to each other. These three axes are typically labeled X, Y, and Z, with the positive x-axis pointing out of the page, the positive y-axis pointing to the right, and the positive z-axis pointing up. Just as in two dimensions, the point where the three axes meet is called the origin. The origin corresponds to the ordered triple 0, 0, 0. The three axes can be oriented in any way, as long as all three axes are perpendicular to each other, and they conform to what is called the right-hand rule. The right-hand rule states that if you align the thumb of your right hand pointing in the positive direction of the x-axis and your index finger pointing in the positive direction of the y-axis, then your middle finger should point in the positive direction of the z-axis. For example, we could arrange the axes so that the positive x-axis points to the right and positive y points up. In that case, the right-hand rule tells us that positive z must point out of the page. Or we could orient the axes with positive x pointing up, positive y pointing out of the page, and positive z pointing to the right. However, the typical orientation is with positive x pointing out, positive y pointing to the right, and positive z pointing up. In 3 dimensions, just as in 2 dimensions, the infinite plane containing the x and y axes is called the xy plane. Likewise, the y and z axes create the yz plane, and the x and z axes create the xz plane. These 3 planes divide the Cartesian space into 8 regions called octants. The octants are numbered 1 through 8 and are typically labeled using Roman numerals. Just as the 2-dimensional Cartesian coordinate system allows us to graphically display ordered pairs of real numbers as points on the Cartesian plane, 3-dimensional Cartesian coordinates allow us to display ordered triples as points in Cartesian space. The elements of an ordered triple corresponding to a point are the coordinates of that point. To locate a point in this 3-dimensional space, starting from the origin, we move along the x-axis a distance and direction specified by the x-coordinate. Then from that point, we move parallel to the y-axis a distance and direction specified by the y-coordinate. And finally, we move parallel to the z-axis a distance and direction specified by the z-coordinate. This determines the position of our point in Cartesian space. Another way to look at this is that the x and y coordinates locate a position on the xy plane just as in 2 dimensions, and the z coordinate specifies the point's distance above or below that position on the plane. Now that we have a way to visualize ordered pairs of real numbers as points on a plane, or ordered triples as points in space, the next step will be to create sets of ordered pairs which represent relations between different types of quantities. If the quantities can be represented by real numbers, then these relationships can be visualized in 2 or 3-dimensional space.
Special thanks to Professor Wang Shimwak. He has given very informative lecture on 3D coordinate system. Now let us come back to our original class. Points on coordinate axis. See student, on x-axis if any point is there, then its y and z coordinates are 0. So A having coordinates x, 0, 0. Similarly, the point on y-axis gives us x and z coordinate 0. So B having coordinates 0, y, 0. And on z-axis, x and y coordinates are 0. So C having coordinates 0, 0, z. Now look at the diagram. Now we'll find out points on coordinate planes. See, if the point A is on the xy axis, see in xy axis, so whose z coordinate is 0. So A having coordinates xy 0. A point B on the yz axis having coordinates 0, yz, whose x coordinate is 0. Similarly, if point C on xz axis whose y coordinate is 0. So C having coordinates x, 0, z. Distance of Pxyz from coordinate planes. See student, distance of P from xy plane is nothing but mod z. See, look at the diagram. What is xy plane? This one is the xy plane. Now, the point is located here. So which is nothing but mod of PL, which is upwards and parallel to Z axis. So the distance of P from XY plane is nothing but mod Z. If it is downwards, then it will be minus Z, but distance is always positive, so we'll write it in modulus. Second, distance of P from YZ plane. Now YZ, X is missing there, so the distance is mod X. And third, the distance of P from XZ plane where Y is missing, so that distance is mod Y. Distance of any point from origin. Look at the diagram, student. So in triangle OLP, which is a right angle triangle, so length OP is equals to under root OL square plus LP square equals to, now OL square is nothing but OA square plus AL square. So write it as it is, plus LP square equals to under root. Now see student, this AL is parallel to OB and LP is parallel to OC. So write it down, under root OA square plus OB square plus OC square equals to OA square is nothing but X square plus OB is Y. So Y square plus OC is Z. So Z square. So length of OP equals to under root X square plus Y square plus Z square. We will see distance of point from coordinate axis. Look at the diagram, student. Now PA is perpendicular to X axis. P having coordinates XYZ and A having coordinates X00. Now by using the distance formula, we can find out PA distance, which is nothing but X minus under root X minus X bracket square plus Y minus 0 square plus Z minus 0 square equals to under root Y square plus Z square. Similarly, we can find out distance PB equals to under root X square plus Z square. Also, the PC distance is under root X square plus Y square. See example, find the distance from 4, -2, 6 to each of the following. Solution. First, we have to find XY plane. The distance from 4, -2, 6 to the XY plane is nothing but mod Z, which equals to 6. The distance from point P to YZ plane is nothing but mod of X equals to 4 units. The distance of point P from XZ plane equals to mod Y equals to mod of -2 equals to 2 units. The distance of a point to the x-axis equals to under root y square plus z square. Substitute the values of y and z there. So we will get which equals to under root 40 equals to 2 root 10. Similarly, student, the distance of point from y-axis equals to y square plus z square, which is in root. Substitute x and z values. So which we will get 2 root 13. And the distance of point to the z-axis equal to under root x square plus y square. Substitute the values of x and y, that we will get 2 root 5. Such examples are asked for MCQ type. Signs of coordinates of point in different octane. See student, we have three mutually perpendicular axes x, y, z. Due to that we have 8 quadrants that are called as octanes. So in first quadrant all the signs are positive. See XYZ plane is there. Then in second quadrant X dash YZ means which has signs minus plus plus. In third X Y dash means Y dash having negative sign XZ positive. In fourth X dash Y dash Z means minus minus plus. In fifth quadrant we have signs plus plus minus. In sixth minus plus minus. In seventh plus minus minus, and in eighth quadrant minus minus minus, since the quadrant is x dash y dash z dash. म्हणजे स्टुडंट जिथे डॅश असेल तो कोऑर्डिनेट ऍक्सिस निगेटिव्ह असेल आणि बाकीचे पॉझिटिव्ह असतील. Example, find the coordinates of the point which is located 3 units behind the YZ plane. Behind YZ plane means x equal to, behind means it is to the back side, means x equals to minus 3. Now the 4 units to the right from XZ plane means y equals to 4, and 5 units above the XY plane. Above XY plane means upward, that is z equals to 5. So the required coordinates of the point is minus 3, 4, 5. Next example, in the YZ plane. See, any point in the YZ plane having x equals to 0. So we have x equals to 0. Now 1 unit to the right of XZ plane means y equals to plus 1. Now x units above the XY plane. Above means which has z equals to 6. So the required coordinates of the point is 0, 1, 6.